Okay, problem 9b asks us to find the eigenvalues and eigenvectors of the matrix A, which is 1, 2, 5, 4. So we always have to find the eigenvalues first. We take the determinant of A minus lambda I, set it equal to 0. So that's going to be, right, we're doing your matrix A minus lambda I is just the matrix A and then minus lambda on each of the diagonal spots. So the determinant of this matrix is 1 minus lambda times 4 minus lambda minus 2 times 5 equal to 0. Multiplying this out, you get 4 minus 5 lambda plus lambda squared minus 10 equal to 0, or lambda squared minus 5 lambda minus 6 equal to 0. Which factors is lambda minus 6 times lambda plus 1 equal to 0. So let's say that lambda 1 is 6 and lambda 2 is negative 1. So for lambda 1 equal to 6, you can solve for the eigenvector in one of two ways. You can either say, okay, I'm going to do my matrix, I guess you can write A times my eigenvector equal to your eigenvalue times your eigenvector. That's one valid way of doing it. So your matrix 1, 2, 5, 4 times your unknown eigenvector equal to lambda 1, which is 6, times your unknown eigenvector. You can use either equation. I'm going to do, usually I use the first row. So first row dot with the first column is 1x plus 2y equal to 6x. That's going to give me 2y equal to 5x. You can solve for y, right? You can say, but really at this point, you're going to let x equal the coefficient of y and y equal the coefficient of x. So your vector, your eigenvector is x is 2, y is 5. You can also solve for y, your y equals 5 halves x, which gives you the eigenline. Alternatively, you could solve this by doing A minus lambda I, so 1 minus 6, 2, 5, 4 minus 6. You do that matrix times your eigenvector equals the 0 matrix. That's the other option. So doing it that way, you get negative 5 times x plus 2 times y equal to 0. Oh, it's the same equation. 2y equals 5x leads us to the same eigenvector. Yeah, that's all there is to say there. So that's the eigenvector for lambda 1 equal to 6, you get the eigenvector of 2, 5. And then for lambda 2 equal to negative 1, same stuff, right? You can do this equation, A times your eigenvector equals lambda times your eigenvector. So 1, 2, x1 equal to, 1, 2, 5, 4 times xy equals negative 1 times xy. So you get 1x plus 2y equals negative x. Subtract x. 2y is negative 2x, or y equals negative x. So x is 1, y is negative 1. It would also be perfectly fine to say the vector was negative 1, 1. Same deal here. Plug in A minus lambda I times v2 equal to 0. Plugging in the negative 1 for your lambdas, you get 2x plus 2y equal to 0. So again, y equals negative x. X is 1, y is negative 1. Great. So that's the answer to part 2b. We have the eigenvalues and the eigenvectors.